want to evaluate the integral from 0 to infinity of 1 over x to the 6 plus 1 dx. And for that, I want to use the following contour. So here along the real axis, then we go up until e to the pi I over 3, so e to the 2 pi I over 6. You will see in a minute why I write it like that. And then back to 0, okay? So first I will find the poles as usual. So we'll set the denominator equal to 0. I get that x to the 6 is equal to -1, which can be written as e to the pi I plus k times 2 pi I. Okay, where k is an integer, of course. Yes, and so I take the 6th square root, or I raise everything to the 1 over 6 power, and I get that x is equal to e to the pi I over 6 plus pi I k's over 3, where k is between 0 and 5, is 0, 1, 2, 3, 4, or 5. Okay. Yes, but you can already notice that only k is equal to 0 will be inside our domain, okay? Because, for example, if we have is k equal, when k is equal to 1, we would have this thing here. We would have 2, 3, no, it would be e to the pi I over 2, it would be here in the middle. So yeah, only k is equal to 0 is in our region, in our domain. So I will separate the path into 3 parts. So part 1 here along the real axis, the part number 2 here, and along this circular axis, and the part 3 from here, so from e to the pi I over 3 to 0. So the first part, path number 1, is my original integral. Okay, I go from 0 to infinity, which is the case. Okay, here the radius is infinity, so r is equal to infinity, and here it is 0. So the path number 1 is easy, it's my original integral. The path number 2, I will set x equal to r times e to the pi I t, so r is the radius. Okay, that here is infinity. We have e to the pi I t, and t is going to go from 0 to 1 over 3, okay, which can be written as 2 over 6. Because yeah, we go from this point here to this point here. We don't go until here or until here. We only go until here, okay? So generally we go from 0 to 1 or minus 1, like we do that, that, or that, but here we only go until here, okay, from here to here. And our dx can be written as pi I r e to the pi I t dt, okay, that is simply if we take the derivative here with respect to t. So if you write everything with respect to t, we have the integral from 0 to 1 over 3, okay, so that is the domain of our t, times pi I r e to the pi I dt, so that is our dx, okay, over r to the 6th power times e to the 6 pi I t, okay. And this is roughly equal, so this r to the 6, e to the 6 pi I t, that is my x to the 6, of course, and there should be a plus 1 here, sorry. But that doesn't change anything, because that is roughly r over 6, so 1 over r over 5, so that is, that will tend to 0 if r goes toward infinity, okay. If our radius goes toward infinity, we will get 1 over r over 5, 1 over r to the 5th power here, and that will tend towards 0. Okay, so we have proven that our second part vanishes. Our first part is our original integral. Now comes the third part, which is a bit tricky. Yes, so we will let our x be equal to t times e to the pi I over 3. Okay, so we will start here basically. And our dx is e to the pi I over 3 dt, so nothing surprising, we just take the derivative. So the e to the pi I 3 here is a coefficient basically, because there is no variable here inside. And our t will be between infinity and 0, okay, because we start at infinity where r is equal to infinity, and we go back to 0, okay? So if I do that, I have the integral from infinity to until 0 to 0 of e to the pi I over 3 dt, so that is my dx here, over t times e to the pi I over 3 to the 6th power plus 1. And now you can notice, so first we inverse the integral, so we go from 0 to infinity, so we have a negative sign in front of it. So here we go from 0 to infinity, we have a negative sign in front of it. We can also take this e to the pi I over 3 outside, because this is a constant, so it is a coefficient, sorry, with no variable inside. So we have our dt here and our 1 here. But now in the denominator, now you can maybe see why we choose to go until e to the 2 pi I over 6 is equal to e to the pi I over 3. Because there is the 6 here, and here we raise it to the 6th power, okay? Both will cancel, and we will be left with this e to the 2 pi I, which is 1. And that's we want, because here we can see, so we have t to the 6, which is our variable, but this e to the pi I over 3 to the 6th power will give us e to the 2 pi I, okay? So this e to the pi I over 3 is, as I said, like this e to the 2 pi I over 6, okay? So the 6 here and the 6 here in this power will cancel, and we will be left with this e to the 2 pi I, okay? It's the same thing as saying that we have e to the pi I over 3 to the 6th power, which will give us e to the 2 pi I, okay? e to the 2 pi I, sorry. And so that will be 1. So we don't care about it. It's like multiplying by 1. And we still have our plus 1 here, that doesn't change. So we can see that basically, so our t is simply a dummy variable, we can name it whatever we want. So this thing here is simply our original integral times negative 1 e to the pi I over 3, okay, the part here outside. We have this part here outside, but the remaining stuff is simply our original integral, but simply we have t instead of x, but that is just a dummy variable, so we don't care about it. So now we can use the residue theorem. We say that our contour integral, so the part 1 plus 2 plus 3 is equal to our original integral, so the part number 1 here along the real axis, plus the part number 2, which is 0, okay, it is 0 here. That is what we proved before for the part number 2 here. We have 1 over r to the 5th power, so 1 over r to the 5th power, yeah, and if r tends toward infinity, we will get 0, okay? And then we have our third part, which is, as said, our original integral times negative, this is a minus here, times e to the pi I over 3, okay? And so we can factor out our integral times 1 minus e to the pi I over 3, okay? So and now we use the residue theorem. We know that should be equal to 2 pi I times the sum of the residues. We only have one pole inside, as I said, that is for k is equal to 0, because k is equal to 1. We are already at pi I over 2. Okay, we would already be here, but you only go like until here somewhere. So yeah, we only have k is equal to 0 inside. So we have our residue. That is again a pole of order 1. So we use the normal formula and not the formula for pole of order n. So we are lucky, so that is simply everything above the bar fractions remains the same, and everything below it, we just take the derivative of it. So we take the derivative of x to the 6th plus 1, which is 6 times x to the 5th power, okay? And the 1 above remains the same, okay? So you have that. And so as I said, we only have k is equal to 1 inside, and so now we plug in our pole for k is equal to 0, okay, like here. So we only have e to the pi I over 6. because the k is 0, so this thing goes away. And so we are left with 1 over 6 times e to the 5 over 6 pi I. Okay. And so now we have that our interval times 1 minus e to the pi I over 3 is equal to 2 pi I times this residue here. So first we can multiply 2 pi I with this 1 over 6 times e to the 5 over 6 pi I, and then we can take this 1 minus e to the pi I over 3 and take it on the other side. Okay, so we divide by it to get our integral. Okay, I hope you see what I mean. We have here we have our integral times 1 minus e to the pi I over 3. Now we want to get the value for our integral, so we simply divide by this thing here, by this 1 minus e to the pi I over 3, okay? And so you get that our integral is equal to 2 pi I times 1 over 6 times e to the 5 over 6 pi I times 1 minus e to the pi I over 3, okay? And so if we simplify a bit, we get pi I here, because there's a 2 here, there's a 6 here, so we get a 1 above and a 3 below, okay, instead of the 6 here, times e to the 5 over 6 pi I times this 1 minus e to the pi I over 3, okay? So that's it, okay? And I think we can simplify maybe even more. We can change some stuff to get a more clean value, I think. Maybe we can write, I mean, it's strange to have an imaginary value here inside, but I'm sure that if you write this I as e to the pi I over 2, okay, e to the pi I over 2, that is I, okay? If you write it like that and that you solve a bit with this e to the 5 over 6 pi I here and this 1 minus e to the pi I over 3, I'm sure that if you solve a bit, you should get a more cleaner value and also remove this I here. That will be converted into something else. But yeah, roughly you should get that value here. So this pi I over 3 e to the 5 6 pi I 1 minus e to the pi I over 3. Okay, should get that, and I'm sure you can simplify even more, but yeah, I don't want to do it now. Okay, you can do it, you can try it if you want and write the answer in the solutions. I don't know if there is a solutions, I don't know, but still that is a valid result for now. Okay, yeah, so I hope that was it. So again, this was a bit harder than the previous one because we have a new contour this time, okay, like a pizza piece. And still we chose our point where we go, or destination, depending on the exponent we have here. So here we have to the 6th power, so we will have e to the 2 pi I over 6, so that when we have this 6 here and this 6 here, they will cancel and we will be left with e to the 2 pi I, so 1, so we will be able to remove this one, basically. I mean, it's multiplied by 1, doesn't change anything, and that's what you want, okay? And then again, you have your proof part. You split your path into 3 pieces, so 1, 2, and 3, and then you solve. And as said, for the third part, it's a bit trickier. You have your x is equal to t times e to the pi I over 3, and you solve accordingly, and you have your coefficient here outside your integral, so minus e to the pi I over 3. And then you see that that is a multiple of your original integral, okay, that goes from 0 to infinity, and there's also your integral r in the first part piece, okay. And so you can use the residue theorem. You know that the second part vanishes. You're left with the first part, and the multiple of the third part is a multiple of the first part, so you can factor out your I here. You get I times 1 minus e to the pi I over 3 is equal to 2 pi I times the sum of the residues according to the residue theorem. and you so you have a pole of order 1. You notice that there's only one pole inside, so for k equals 0, because all others are already outside your domain. So the pole for k equals 0 is somewhere around here. I don't know where precisely. Anyway, so you find your residue, because it's a pole of order 1, so you use the formula for poles of order 1, so that means h of x over g prime of x, okay, so everything above stays the same, everything below the power fraction, so in the denominator, you take the derivative of it, okay? And then yeah, you solve for your integral, okay, so you divide by 1 minus e to the pi I over 3, okay, you divide by that, so you get your integral alone here, and so you have everything else on the other side, and then you can solve a bit, and I said maybe you can even solve a bit more, but I don't know, so I will let it like that. Okay, so at the end you should have pi I over 3 times e to the 5 over 6 pi I times 1 minus e to the pi I over 3. Okay, so a bit complicated, I know. Yeah. So thanks for watching.